Hello and welcome to another Maths Support video. So today we're going to be talking about confidence intervals. What is a confidence interval, I hear you ask? Well, you've come to the right place. The clue is really in the name. It's a measure of confidence about an interval based on a population parameter. So we have a population parameter and we want to be sure it's within a certain interval and we can be confident of that. So the best way to see this is through an example. So if I just direct you over here, we have an example. We've got two columns of data here, an X column and a Y column. And let's say these are IQ scores from a test. So this is a student's individual IQ score. And this is it a week later after they've done the test again and revised. So let's see if the mean IQ test score changes. Underneath here, we've just got a sum for each of the individual values there, and same here for our Y column. So to do a 95% confidence interval, we first need some assumptions. In this case, we're going to be assuming that the values are independent. So one person's IQ score is independent of another person's IQ score, which makes sense. We can also assume that our data is normally distributed. Now we know that in this case, but you may need to check your own data with certain tests to check if that really is the case. And we can also assume in this case that we've got equal variance because one person doing a test and doing it a week later, we can assume that their variance is going to be the same. Okay, and we want a 95% confidence interval for this data. Right. So, we need some statistics. So the first statistic we need is easy. We just want the number of observations in each column. So in our X column, we've got 6 observations. In our Y column, we've got 6 observations. So we can say our NX and our NY are 6. Our X bar, well, that's just the sum of the observations in that column. So for X, this is 660 divided by the number of observations, which is 6. And we say that is 110. Same for our Y, we can calculate that in the very same way. Next thing we need is our xi squared. So this is the individual observation squared added to the next individual observation squared. So 101 squared plus 115 squared, etc. So we get that to be 73,000 in our X column, and in our Y column we get that to be 81,112. Okay? Now we need our S squared values. This is our estimator of the population variance for each column. So for this, we need 1 over nx, which is the number of observations, minus 1, multiplied by our xi squared minus the number of observations multiplied by the population mean squared. So if we put these values in, we've got 1 over 6 minus 1. We've calculated this over here, so that's 73,000. Minus 6 times x bar squared, which would be 110 squared. And we can calculate this to be 80. We can do our sy squared in the very same way. So we can say that's 75.2. And now we need a combined estimator, our sigma squared hat for this value. Because we're assuming equal variance, we can then pool this in the form we have here. So what we're saying is it's n, which is our observation minus 1, multiplied by our sx squared. Same for sy, and this is divided by our number of observations totaled minus 2, because we have 2 columns data. So let's plug that in. So we would have 5 times 80 plus 5 times 75.2 all over 10, which would give us a value of 77.6. Okay, right, next thing we need to do is start thinking about our t statistic and for our confidence interval. So the first thing we need is our significance level alpha. And now we wanted a 95% confidence interval. So our alpha, our significance level, would be 0.05. We then need to divide this by 2 because we're doing a two-tailed test. So we get that to be 0.025. And then because we want the 95% confidence interval, to look up in our test statistics, we need to take 1 minus alpha over 2, which is 0.975. Right, so then we plug it into this form. So we've calculated what 1 minus alpha over 2 is, which is t 0.975. And then we've got this value as well, which we calculated earlier. So it's 6 plus 6 minus 2, which is just 10. And then you can go away and look that up in a table if you'd like. But I've got it to hand here, and it's 2.228. Right, so we're on the home straight now. So all we need to start thinking about is putting this into our confidence interval form, our formula here. So we need our x bar and our y bar, and we take that away, see the difference. And then we're going to work out two values from this, one with a plus, one with a minus. We multiply our t statistic by the root of our s squared estimator, which we calculated earlier, open brackets, 1 over nx plus 1 over ny. Right, so let's plug this into that form. So we have 110 minus 116 plus or minus 2.228, which you should have looked up in your tables. And then you've got 77.6 as our s squared, and this is then just 1 over 6 plus 1 over 6. And then if you run off with a calculator, you'll just get the value minus 17.3314 for our lower confidence interval end, and then 5.3314 for our top end value.